Have you ever stared at a circuit diagram and it just felt more like a maze than a map? Yeah, you're definitely not alone. So today, we are going to crack the code on one of the most common puzzles in all of electronics, the combination circuit. All right, let's dive in. I mean, look at this. This is the reality. Real-world circuits, like what you'd find inside an industrial panel like this one, they're never just a simple series or a simple parallel line. Nope. They are a complex, tangled web of both, all mixed together. And that really brings us to this central challenge, right? It's the thing that stumps so many of us. When you're looking at all that complexity, how in the world do you solve a problem when you don't even know where to begin? Okay, so let's get into the tangled circuit problem. And we need to frame this correctly, because this isn't just some abstract theoretical puzzle. We're talking about the real world here, and maybe more importantly for some of you, on an exam. Misunderstanding these circuits? Oh yeah, it has serious consequences. So, what's at stake? Well, pretty much everything. On an exam or, a real diagnostic test, one tiny error at the very beginning doesn't just cost you a point. No, it cascades. It's like a domino effect. That first mistake just topples every single calculation that comes after it. So getting that initial identification right, it isn't just half the battle. Honestly, it's the only way you're going to win. But here's the good news. There is a secret to taming this complexity, a really powerful method that can turn that tangled mess into a simple, totally solvable problem. And it's all about the art of simplification. See, the secret isn't about trying to solve the entire puzzle all at once. That's just a recipe for confusion and a major headache. No, instead, your first job, your only job really, is to simplify it first. You break it down piece by piece until it's something you can actually manage. And this brings us to this really elegant, super systematic approach. It's called the reduction method, and it's basically a three-step mindset. Step 1, you identify the circuit's different parts, the parallel bits, the series bits. Step 2, you reduce the circuit step by step, collapsing it down into one simple equivalent resistor. And finally, step 3, you backsolve. You take that simple version and you work your way backward to find all the original details. All right, so theory is great and all, but let's actually put this method into practice. We're going to solve one of these step by step. But hang on, before we start, we need to make sure our tools are sharp. So let's do a super quick review of the fundamental rules. For series circuits, super easy. Resistance just adds up, and the current is the same everywhere. For parallel circuits, it's kind of the opposite. Voltage is the same across all the branches, but the current splits. Honestly, getting these rules down cold is the key to everything we're about to do. Okay, here it is, our puzzle for today. This is a classic combination circuit. You've got one resistor in series with a pair of resistors that are parallel to each other. This is like the perfect training ground for our reduction method. Okay, so step 1. Here's what's so cool about this method. Where you begin. You don't start at the beginning, at the power source. No, you work from the inside out. Your very first move is to find the smallest, most self-contained part of the puzzle. In our case, that's the parallel section. We need to reduce that part first. So how do we do that? We calculate something called equivalent resistance. It sounds fancy, but all it means is, what's the value of a single resistor that would do the exact same job as that parallel pair? And hey, for two resistors in parallel, there's an amazing shortcut formula. It's called product over sum. You literally just multiply the two resistor values on top and add them on the bottom. So easy. And boom, this right here shows you the power of reduction. Just like that, we've taken that tricky parallel section and swapped it out for one single, simple equivalent resistor. And look what we have now. The puzzle has become a basic series circuit, so much easier to deal with. Now we just add up the series resistors to get our total resistance. And this part is super easy. Since it's now just a simple series circuit, we just add the first resistor to that new equivalent resistance we just figured out, and that's it. That gives us the total resistance, our total for the entire circuit. The puzzle is now as simple as it can get. Okay, final step, we gotta backsolve. We take that total resistance we just found, and using good old Ohm's law, we find the total current coming from the power source. Then, we just work backwards. We retrace our steps. When we get back to that parallel part that we simplified, we use our rules to figure out exactly how the current splits between those two original branches. We just keep working backwards until every single voltage and every single current in the original complex circuit is found.
All right, you've got the core method down now, so let's add a couple of pro-level shortcuts to your toolkit. I'm talking about the tools a master uses to solve these things with real speed and precision. Okay, two big ones here. First, for series circuits, you've got the voltage divider rule. This thing is awesome. It lets you find the voltage across any single resistor in a chain without having to calculate the current first. Total time saver. Then, for parallel circuits, you've got the current divider rule. This one is an absolute lifesaver. It tells you exactly how the current splits up between the different branches. And just remember the logic. It's simple. Electricity is lazy, right? It follows the path of least resistance. So the branch with the higher resistance, it's going to get less current. Makes sense. So, we've solved the puzzle, but hold on, we are not done yet. There's one final and you could argue most important step for any pro. You have to verify your work. You need to know with 100% certainty that your answer is perfect. And your first master tool for checking your work is Kirchhoff's voltage law, or KVL. Now, this is built on a really simple but powerful idea. All the voltage the power source puts in has to get used up by the components in the circuit. You can't just create or lose voltage out of thin air. So what does that mean? It means if your calculated voltage drops don't add up perfectly to the source voltage, you've got a math error somewhere. It's that simple. And your second tool is Kirchhoff's current law, KCL. This one is also common sense when you think about it. Current has to go somewhere, right? So at any junction, any point where the circuit splits, the total amount of current flowing in has to equal the total amount of current flowing out. Current can't just vanish into thin air. This is the ultimate double check for all your current calculations. And this is why this all matters so much. These checks are designed to catch those simple arithmetic mistakes before you finalize your answer. So really, don't think of KVL and KCL as some big, complex laws. Think of them as your personal safety net. They're what guarantees you hand in a perfect solution every single time. So let's just bring this all home. On one side, you have the common mistakes, things like adding parallel resistors like they're in series, or just losing track of which value belongs to which part of the circuit. That's the path to getting it wrong. But on the other side, you've got the pro tips for success, and they're really just simple habits. Label every single step clearly. Redraw the circuit as you simplify it. And always verify your answer with KVL and KCL. You know, when you step back, what we've really learned here is way more than just circuit analysis. It's a method for deconstructing any kind of complexity. You now have the framework to take any tangled puzzle, simplify it down to its core, solve it, and then prove that your answer is right. So the only question left is, what puzzle are you going to solve next?